So our set theory is very just basic. Okay, now how does all of this apply to probability? Basically you have to remember one very important thing, that probabilities are fundamentally assigned to or attached to sets. Probabilities are numbers which are attached to sets, right, of any kind. Those sets can be sets that you start out with, such as A, B. They can be the unions, intersections. Remember, all of these operations like unions, intersections and complements, they give you new sets, right. So if you say you start with probability of A, right, then you also must think of the probability of A complement, right. So that is formalized in this notion of a sigma field or a sigma algebra, right, which sort of says, okay, if given a sample set capital omega, what are the sets, right, to which I can assign probabilities, right. So that is the next important point that we are going to look at. So let me start here. The concept of a sigma algebra, right, sigma field. So these are, so what the F is basically a collection of sets. To which probabilities are, right. So as such it occupies a very important theoretical, right, position in probability theory. In fact you talk of triad, right, you talk of omega, you talk of the script F, and you talk of the probability function P, right. So every probability experiment is omega Fp, right. So what is this F, right, what are the rules to form this collection is F, and basically F should follow some rules which allow it to be called a sigma field, right. So the rules for F, again I am saying this at a very intuitive level, right, not very rigorous, right. One is that omega and phi are always in this F. Now note this use of this notation here, element means it belongs to, I should have said it earlier itself, small omega belongs to capital omega, right, E, that notation we will use a lot, okay. So we will use it here now, right. So note, right, capital omega is just a set, as a universal set like anything else, it always has to belong to capital F. So the simplest F is something which only contains, as it turns out, only these two sets. The universal set, the certain event omega and the null event, I mean the null event, right. So if you want to assign probabilities, the standard thing to say, well, is that I will always assign 0 to this and 1 to this, right, but that is not very helpful because it does not talk about anything in between, right. You know for example that the null event never happens, right, and the certain event happens always, big deal, right. So you have to go further. So what if you want to include a certain element A in a set, that means A in F, that means you also have to include A complement, right. So if you include A, you must also include A complement. That means that you cannot say that I will only assign A a probability, I will not assign A complement a probability, right. Okay. Then if you want to include A and B in F, then you must include A union B also. And by De Morgan's law, right, with the fact that you have to do complements, you can automatically, I mean, or whatever, show that this must include A intersection B also. So up to this point, well, I mean, and okay, so what if somebody says I have A1, A2, A3 again, right? You know that you can form the unions of A1, A2 with A3 and so on, right? So obviously the collection will keep growing, right, as you increase the number of sets in F. Okay. What in, so that this is basically, this framework is basically sufficient to deal with a finite collection of sets in F, but we also need to separately list out the case of a countably infinite collection of sets, right. So let me include that point here. If ai, again this is a notation which we will use, right? If ai 1 to infinity is a short form of saying a1, a2, a3 up to infinity, if each are defined, if you define this infinite collection with ai in f for all I, no matter how, right? Now how do we define, what would be a good example of this? First, of course, you must have, right, an experiment which supports an countably infinite collection. For example, the coin tossing until you get a head type of experiment, right? I'll just simply write the result and then we can look at it. Then the union of these sets must also be in F. Remember, I might write expressions like this, but this capital omega is sitting on top of all of these unions and intersections, right? So this countably infinite union that I've written out there, right, obviously has to be no bigger than, or can be no bigger than capital omega. So if capital omega is well defined, there is no reason to get afraid of that left hand side, right? For example, getting a head on the second, an even number of well, I would say ai could be second toss, fourth toss, sixth toss, so right, so on, right? That what would the union be? It would be getting ahead on an even numbered toss, right? So that also has to be in F. So this is stated sometimes as a distinct rule, right? Apart from this would really come into effect only if you had the right an accountably, at least a countably infinite number of elements in omega. It also, right, applies, right, when you have an uncountable number of elements in omega as well, because that's also a case that you can form an infinite collection of sets. But remember, even if omega itself is uncountable, this is a countable collection. Anything with you index with an integer has to be countable, right? And by contrast or whatever, you cannot index an uncountable set with an integer, right? Or right, you cannot use integers to count uncountable quantities, right? So if I write ai, it means that the collection ai is countable. Okay, so these rules, right, are the bedrock again that are used to form define a sigma field capital F, right? And we will assign probabilities to every element of in continuation of this, probabilities assigned to each member, I would say, I won't say element, to each member of F, which is some set, right? That is the importance of F, right? Yesterday we talked about the total number of sets, right, when the number of elements in omega is capital N. All of you said 2 power n, right, which is perfectly correct. So the simplest construction in such a case would be to say F consists of all subsets of capital omega, right? So to make our life easier, right, we are not going to discriminate, right, in the case, which is what is done without putting it in so many words, right? In all examples of probability theory, they implicitly do it, that's the word I am looking for, right? They implicitly say, without saying exactly saying so, that any set can be assigned a probability, right? So when F is countable, not even necessarily finite, when omega is countable, right, that is discrete, then F will be so called, F will be defined as this equal to with a triangle on top you are going to use for definition, right, by definition. Then F will be by definition the power set of, what is this power set, i.e. the set of all, or let me not use the word set here, I will just say collection of all subsets So this terminology power set is very important and occurs quite often. So yesterday we said if capital omega has n elements, then the power, it has 2 power n subsets, so those will form the power set. When n becomes infinity, right, that is the countably infinite case, you still have the same construction, except that it is an interesting point here. This 2 to the power of countable infinity is our bridge from countable to uncountable. It is an interesting side note that you should all be aware of, right. Have you seen this point? 2 power n as n becomes infinity is actually the number of points in the real, in some segment of the real line, right. Go and read it up if you are right, if you find if you are hearing this for the first time, right. That is a bridge. You go to Cantor's argument, or where I do not know who is the mathematician, I am not a mathematician, so I have to throw up my hands and say right. These are things which I have picked up just by reading this any number of times, but right, even this morning I checked up something and the same result was there, right. This 2 power n, that is that capital N, when it goes to infinity, that number becomes uncountable. Okay, and it actually makes sense, right. If you look at all the binary representations of the points between say 0 1, what would you do? You put a binary point and then you write strings of zeros and ones, right, to infinite precision, right. So how many binary digits would you use? You use an infinite number of them, right. What is the total number of such binary digits? 2 to the power of that infinity, right, not any infinity but the infinity which is the set number of natural numbers, right. And you claim that every real number has a representation of that kind, between 0 and 1 say, right, has a representation of that kind at point 0 1 0 1 something, right, going up to infinity. So that is why intuitively you can understand, right, that the 2 power infinity does give you a representation of the, right, a count of some in a way, in a loose sense it tells you how many uncountable numbers are there in the basic, right, set that we start with, that uncountable set that we use, right. Okay, so I am not going to let me just not write that down here, but so when omega is countable, right, we will always use the power set of this omega as the f. So that means a lot of work is saved for us. We do not have to scratch our head in every particular probability experiment, say what is this f, what are the sets to which I am supposed to assign probabilities, right, which sets am I not supposed to assign probabilities. You do not have that confusion for the time being. However, I have to warn you, this statement cannot be used, right, for deep mathematical reasons. This statement will not work in the case that omega itself is uncountable, and that is where we get into really slippery ground, right, as far as the theorists go, right. Luckily they worked out what we need to use, and we will just stick to that. I will come to that point later in the course, but it has all been worked out for us, right. That is the nice thing about it. We do not have to get into many more complications than we need to, but this statement will not hold. What will hold, we will save that for then, right. So since I have a few more minutes, let me continue. Every minute is precious, remember, right. So are we okay so far? Does anyone have any questions? You can please ask questions, it does not matter if you are on camera or not, right. As I said, the camera is not going to focus on you, it is only focusing on me. Are we okay so far? Okay. What is then probability? Quantitatively, right? This probability function p, which we will write, remember this p is going to be, sometimes it is written with 2 vertical lines, but it is little difficult to keep carrying it on, so we will just mostly stick to one vertical line for the p, right. But I just wanted to, when the first time I am writing in this course, right, to emphasize the importance of this function, I am writing it like that, okay. So fundamentally this p is a function that maps takes you from this, right, set f to what? What is it? The p itself has a domain and range, right. You all know about domains and ranges of functions, right. So, the domain of P is this f, which means every set in f has to be assigned a number, and this number is in the closed interval 0 to 0 1. So, that is basically probability, right, and just stripped of all, right, all other the esoteric connections or whatever, right. It is just a number at this point, right. Now, of course, it comes it is a very loaded number, it is not just a simple number, but right, this is what you have to first understand. So, i.e. PA, right, the probability of an element of an event A which belongs to F is a real number between 0 and 1, such that again we have rules for assigning probabilities, right. So, what are the rules that we have for assigning P's, right? P of phi is 0, P of omega is 1. Now, since we want probabilities to reflect some useful measurable quantity in the real world, or approximately be an approximation or estimate of some probability of some number in the real world, right. So, an impossible event will never occur, right. Phi, as I said, right, in probability is the impossible event, right, the null event or the impossible event. So, that always has to have 0 probability. Okay. Now, why are we giving the set omega, the universal set? By convention we give it unit probability, right, although the theory will will work reasonably, will work okay, I am sure it can be reworked if you have any positive number as the probability of omega, right. But there is a important physical reason for making that maximum number equal to 1. We want it to be some finite number, right, and there is a lot of intuitive sense, right, and I mean a lot of things fall into place if you make this equal to 1. So, that is the universally used convention which we are going to obviously follow here, right. So, therefore, no probabilities can exceed 1 by definition, right. And then the other important rule is that, right, we will just say it and close for today. If, right, if A and B are, that is if two sets in F are exclusive, are ME, then P of A union B, the union, the probability that is attached to the union must be what? The sum of right. So, these are the basic rules. We will expand on this tomorrow, right. We are running out of time today, so we will stop here.